This is the Fortran code, which works based on different algorithms to find the roots of functions. Here we have the definition of parameters. F is the function. You have to find the roots or the zeros of this function. Fp is the derivative of the given function f. This derivative is used in the Newton-Raphson method. G is the function defined in the fixed point. G of x should be equal to x. This is the platform for the fixed point. RAND is the random number generated for the Monte-Carlo method. Exact is the exact value of the roots. P0 and P1 are two previous iterations. ERR is the error of computing the roots. Error limit is the threshold of convergence. P new is the new guess or the new iteration for the new prediction of the roots. F double is the function which has a double root. It means that the function itself and its derivative are both 0 at the root, and fp double is the derivative of this function which has a double root. We have I as a counter. These are switches, fixed point, which can activate different algorithms, which, for example, the fixed point method, the bisection, the secant. Of course, the Newton-Raphson method is a special case of the fixed point. So we don't have a separate switch for this method. So let's start from the first one, which is the Monte-Carlo method. Let's activate. Here is the algorithm for the Monte-Carlo method. The exact value is this one. The function is defined here. This is the function. X times x times x plus 4 times x minus 10. And we are going to find the roots of this function in the interval between here 1 and 2. There is a unique root for this function in this interval. And the Monte-Carlo method works based on generation of random numbers. So n is the number of random numbers generated to reach the error limit. This part generates a random number and saves the results in the parameter rand. This relation here maps the generated random number, which is something between 0 and 1, maps this random number into the interval between P0 and P1. For example, if the generated random number equals 0, the P new will be P0, and if the generated random number equals 1, then the new value will be equal to P1. So, and this part tries to find the next interval. If this function or this expression here returns the sign of the function f at the new point, our new point, a guess of the roots, P new. The result of this part will be -1 or +1. And also based on the sign of this function here. And also this part returns the sign of the function f at point P1. Okay, if the sign of these expressions are not identical, so the result will be something less than 0, then the new value of the P0, which is the left side of the interval, will be P new, else the P1, which is the right side of the interval, will be the new guess of the root. This way you can decrease the interval and then after generating enough number of random numbers, you will reach the roots. Okay, this is the error, the relative error, and this part writes the result on the screen. Let's run the code using 150 random numbers. Okay, you see here we have this is the converged value of the numerical root. This is the exact value, and we can see the variation of the relative error. As you see here, we have a smaller relative error in comparison to the next guess. So this shows that the convergence of the Monte-Carlo method is not monotone. So we may have an increasing trend in the error by increasing the number of generated random numbers, and also consider that we need 25 random numbers to reach our threshold of convergence. So let's write this for the Monte-Carlo method. We need 25 iterations to reach the specified threshold of convergence. Okay, let's start the next one, which is the bisection method. The function is similar to the previous case, so the exact value of the root is the same. We continue the loop until we reach the error limit. And the bisection method is very similar to the Monte-Carlo method. The only difference is the next guess of the iteration. In the Monte-Carlo method, the next guess is generated based on the random numbers, but here we compute the next iteration by averaging the values of P0 and P1, or the next iteration is the midpoint of the interval. So the first guesses are P0 equal to 1 and P1 equals 2, and the next guess will be the midpoint, which is in this case 1.5. And to continue the process, I need to compute the next interval. So I will check the signs of the value of f at two ends of the interval. The product of the signs is negative. It means that the left side of the interval should be the new guess, P new, and else the right side should be the new guess. This way you may easily compute the next guess of the root. This is the computation of the relative error. Let's run the code. Okay, as you see, we need 9 iterations to reach the threshold of convergence. Again, you see the relative error it has been increased, and this is similar to the Monte-Carlo method. This fact shows that the convergence of the bisection method is not monotone. And 9 iterations, so let's write the result here. For the bisection method, we need 9 iterations to reach the threshold of convergence. The next one is the fixed point. As you know, the Newton-Raphson method is a special case of the fixed point. So here, at the end of my program, I need to compute the derivative of f or f prime. Here in this case, the fp should be 3 times x plus 8 times x. And also, I need to compute the fixed point function, which is shown by g. You may easily change the g function, and you may try different functions. Here I have written 4 different g functions. Let's try the first one. The result shows that the result of the error, you see here, this is divergence. So selecting this function results in divergence. So this is not a good choice. Let's check the other one. All of these g functions can be easily obtained based on the given function, and constructing a platform such as x equals g of x. Again, divergence, or yielding something like square root of -1. The next one. So, but the convergence is somehow monotone, because as you see, we have a decreasing trend in the relative error, but in 14 number of iterations. And the last one, reaches the results in 5 iterations. So by choosing different g functions, you may have different rate of convergence. Here, for the fixed point, 2 of them divergence, and the third one 14 in number of iterations, and the fourth one 5 iterations. Okay, let's try the Newton-Raphson method, which is a special case of the fixed point. And this one is the formula for the Newton-Raphson, x minus f over f prime. This is f, and this one is the derivative of the f. Okay, as you see, 3 iterations. That's amazing. This is a second order method. So here the Newton-Raphson just needs 3 iterations to reach the convergence criterion. Secant method, which is a special case of the Newton-Raphson method. As you know, the problem or the disadvantage of the Newton-Raphson method is the need to compute the derivative of the function. So here I just replace the derivative by its approximate value based on finite difference approximation. So for the second method, you need the two initial guesses. So P0 is 1 and P1 is 2. Then you can compute the next guess using the formula for the second method, and the error here, the relative error. And then you will replace P1 in P0 and the new guess for the root in P1, and then continue to process until you reach the convergence threshold. Then I can activate the second here to find out the number of iterations. Again, 5. So the advantage of the second method is that it's only elimination of the need to compute the derivative of f, but the rate of convergence is slower in comparison to the Newton-Raphson method. And the last one is to try the Newton-Raphson method for a function which has a double root. It means that the value of the function itself and its derivative both are 0 at the root. So here I will use the this one, which is the f double. F double is a new function like this, p of x minus 1 minus x. And this is the derivative of this special function. As you see here, the root is x equals 1. So both the function itself and its derivative are 0 at x equals 1. So the root of this function is the double root. And of course, I have to change the value of the exact root, which is 1. You see, we need 16 iterations to reach the roots by using the Newton-Raphson method. As you know, the Newton-Raphson method is a second order method which is very fast in convergence. This is strange. This problem originates from the root, which is a double root. Then I can easily now add a magic number here, 2, which is the degree of the root. This is the double root because the function and its derivative are 0. And the second derivative is not 0 at the root. So the degree of the root is 2. And then I can run the code to find out the new number of iterations based on, 3 iterations. And this shows that this new version of the Newton-Raphson method is something in order of 2. And here I have the Newton-Raphson for the double roots, 16 the standard Newton-Raphson method, and 3 for the modified Newton-Raphson method based on the order of the root. Based on our comparison, as you see, the Newton-Raphson method is the most efficient algorithm, but for the simple roots. And for the double root or multiple roots, you need to modify the method. The Monte-Carlo method, as expected, has a very large computational cost, and you need to find the value of the function at a very high number of random numbers.